Thank you. It was recording earlier, but then it stopped recording. All right, thank you very much. So let me just quickly recap where we were. So this is a rapid introduction to L functions. The goal is to do just enough so that we can start when small begins and really get into the problems and have enough time with the 9-10 weeks to make some significant progress. So we're going to start with the Riemann zeta function, which is defined as the sum over the integers 1 over n to the s, and this converges if the real part of s is greater than 1. It turns out that it also equals the product over primes of 1 minus 1 over p to the s inverse. And there are two main ingredients to the proof. The first is the fundamental theorem of arithmetic, that you can write any integer as a product of primes in increasing order uniquely. And the other is the geometric series formula, that if the absolute value of r is less than 1, then 1 plus r squared plus r cubed and so on is equal to 1 over 1 minus r. And one of the reasons this is so valuable is that we have this local information, what's going on at the primes or the integers, and we build up this global object. And the hope is that if we can somehow understand this global object in another way, we can use that to deduce information about the primes, the building blocks. There is not that much mystery in the distribution of integers. We actually even have a formula for the nth integer, it's n. We know the spacings between adjacent integers, it's always 1. These are truly trivial problems. The same problems with primes, however, is extremely interesting. And so the idea is, can we somehow go from knowledge of the integers to knowledge of the primes? And so there's a lot of things you can do. The first is if you look at the limit as s goes to 1 from above of zeta of s, this looks like the harmonic series which diverges. Therefore, there exist infinitely many primes. And in fact, with a little bit more work, you could even get some statements about how many primes there are. So whenever you give introductory lectures, it's often nice because you can play fast and loose with the mathematics. You don't have to worry about making everything rigorous. The goal is to give a rough sense of what's going on. So if I have a sum over n less than or equal to x of 1 over n to the s, that's approximately the same as the product over primes less than or equal to x of 1 minus 1 over p to the s inverse. Okay. Whenever you have a product, you should have a Pavlovian response, take logs. And the reason is, we've taken lots of classes in terms of dealing with sums. We know how to work with sums. We're familiar with them. The log of a product is the sum of the logs. So we'll take logs, we'll set s equals 1, and we get that the log of the sum of n less than or equal to x of 1 over n, it's approximately -1 sum p less than or equal to x of the log of 1 minus 1 over p. And I'll recall Taylor series, the log of 1 minus x, its first order Taylor series is -x. So this should be approximately, the negatives will reinforce, the sum of p less than or equal to x of 1 over p. And if you remember your harmonic series, anybody know what the sum of 1 over n and up to x is approximately?
Log x.
Log x. So we get log x is approximately the sum of p less than or equal to x of 1 over p. And this actually is correct. So just by looking at what the zeta function is doing as s goes to 1, gives us not only that there are infinitely many primes, but a good estimate as to what their growth rate is. It's so much that the sum of their reciprocals diverges. This is very different than the sum of the reciprocals of the squares. The sum of 1 over n squared is pi squared over 6, that's finite. So there's a lot more primes than integers. So already we're getting a lot of information about the primes just by looking at what's going on when s heads towards 1. Now I remarked a moment ago that the sum of 1 over n squared is pi squared over 6. Well, this turns out to just be zeta of 2. But we know the Riemann zeta function is the product over primes of 1 over 1 minus now to be p squared inverse because we're taking s equals 2. What kind of number is pi squared over 6? So
transcendental.
Transcendental. So pi squared over 6 is transcendental. We actually only need something a little bit weaker. We just need that's irrational. If there were only finitely many primes, what could you say about this product if only a finite number of primes
It's rational.
is rational? So what you can get from this is there must be infinitely many primes. So zeta of 2 being irrational implies that there are infinitely many primes. At one point, this was responsible for the worst theorem I had ever proven in my life. I proved that zeta of 2 irrational implies that the number of primes less than or equal to x is greater than log x. So the question was, we know that there has to be infinitely many primes. Can you get anything about the growth rate? And I was able to show that it's at least log x. Does anybody know why this result is so bad?
Because it actually should be about x over log x.
So 1 is the prime number theorem. We call this quantity pi of x is approximately x over log x. So first off, it's really far from the truth. Okay, so that's bad. There's another reason, however, why it's bad. If you are familiar with Euclid and his proof by looking at, if there's only finitely many primes, multiply them all together and add 1, and that's either prime or divisible by the list, that leads to pi of x is greater than log x. So it's worse than Euclid. But the real reason it's really, really bad is my proof uses a result on the least common multiple of the numbers 1 through n, which relies on the prime number theorem. So the paper I was using used the prime number theorem to prove a result about the least common multiples, which then was used to prove a result about how irrational pi squared over 6 is, which I then used to prove that there's at least log x primes. So in other words, starting with the fact that there are x over log x primes, I'm able to prove that there's at least log x primes. You will have to work very hard this summer to get a worse result than I have just shared with you. The reason I like to share this story is it highlights how careful you have to be when you theorem shop. When you just take a paper and just take the results from it without really looking at it and checking everything. You will find that I have an interesting sense of humor. I remember when I was a postdoc somewhere, a graduate student showed me their thesis and they were very proud and they were showing me their results because it's in the area of my main line of research. There were many ways I could have handled this. This may not have been the best way to handle it, but it did teach the student a lesson. I looked at it very quickly. I flipped through it and said, really, very, very nice. Do you know that half of your thesis is wrong? And the jaw just drops because this is not what you want to hear right before you defend. And the reason I could tell so quickly that the result had an issue was I knew which paper this graduate student was quoting. And this paper says early on, we assume that k is congruent to 0 mod 4. If k is 2 mod 4, there's a trivial modification of an extra minus sign. That should have been before every theorem in the paper to remind the reader that k is 0 mod 4 or 2 mod 4. It took less than a minute to fix the student's thesis. You just had to add an extra minus sign and everything was fine. But it really taught the lesson. This is a problem we're going to have over the summer. We have 9 to 10 weeks. How much time do we want to spend learning mathematics? The more mathematics you learn, the better. But the danger is you spend so much time reading, you don't spend as much time doing. And so what I want to try to do is I want to try to balance these competing influences and spend enough time teaching you math and having you do guided readings, but not so much time that you don't have a chance to actually explore and do things yourself. The other advantage of doing things yourself and not doing so much reading is you don't have the blinders on of going down the path that other people are setting up for you. And that if you are a little bit unaware of what's out there, it's actually sometimes more advantageous. And in fact, in one of my calculus classes today, we were doing the different ways to tell if a series converges or diverges. And one of my students had a different way to use the comparison test than I was using. And it was absolutely great to see that. There's often more than one way to arrive at a result. All right, so this is hopefully giving you some sense of why we care about the Riemann zeta function, its connection to primes, the primes of the building blocks. Really, what's going on at a fundamental level is this idea called generating functions. And the idea is you take a bunch of objects that you have some idea about and you put them together, and from that, you build a more interesting object. So I'm going to pause for a moment, Zoom recording. So I want to talk about Binet's formula. This is one of my favorite formulas in all of mathematics. And so there's a couple of ways to define the Fibonacci's. I'll do the standard one, 1, 1, 2, 3, 5, 8, 13, and so on. And so each number is the sum of the previous two. And here is an explicit formula for the nth Fibonacci number. It allows you to jump to whatever number you want. Now this is absolutely amazing. What kind of number is the Fibonacci's? Are the Fibonacci's?
Integers.
Integers. So imagine you have a police lineup, some number has mugged you and they've got a couple of suspects and you're trying to decide which one is it. Does this look like an integer? You've got radicals, you've got division, everything miraculously cancels. As a nice exercise, what can you replace the root 5 and the 2 by and still have an integer? So again, whenever you're seeing a mathematics lecture, always try to think, what kind of problems can I create from this? So what I'm going to do is I'm going to create a generating function. So I have the recurrence relation, fn plus 1 is fn plus fn minus 1. I'm going to form the generating function, g of x is the sum of fn x to the n. Now at first, it seems like this is a stupid thing to do. I don't really know the Fibonacci numbers, so how am I going to say anything about this function g of x? Well, I actually know everything about the Fibonacci numbers once I give you the recurrence relation and I give you the initial conditions, 1, 1. Everything is determined from this point onward, or if you want, 0, 1, 1. So how can we extract information about the Fibonacci numbers from g of x? Well, the only way this is going to work is if we have some global information about g of x. So if I sum from 2 to infinity of fn plus 1, xn plus 1, if you've ever taken a class in differential equations and seen the series solution approach, it's basically a game of playing with indices. And so if I look at this, well, I can write fn plus 1 as fn plus fn minus 1. Okay, that's probably why I'm writing it as n plus 1, x to the n plus 1. And now here I have fn xn plus 1. What might you want to pull out of this expression?
An x?
An x, because then it's going to start looking like g of x modulo a few terms in the beginning, and this one you'd pull out an x squared. And so, when I rewrite it, I shift my indices so that everything is going with now n's. I pull out an x and an x squared, and then I just add the stuff that I need to make each of these a g of x. So this is g of x if I subtract off the x and the x squared terms, and similarly for over here. And so now I have g of x on both sides. And so what I can do is I can bring all the g of x's over to one side and solve. This is the bring it over method. You might have seen this in some integration problems where if you're integrating things with cosine, you integrate by parts twice, and then you have your integral on both sides of the equation with a coefficient other than 1. You bring it over and then you can solve for the unknown integral. So we get g of x is x over 1 minus x squared. All right, well, you might try to expand this using the geometric series formula saying, I can write this as 1 minus r, where r is x plus x squared. That would be a bad thing to do because this is not a homogeneous polynomial. The x and the x squared have different terms, so when you expand it out, it's going to become a nightmare to collect it into a nice Taylor series. So instead, we do what is usually considered the least favorite technique from integration theory. So what technique did you hate the most? Or would your friends hate the most?
Partial fractions.
Partial fractions. There actually is a use for partial fractions. So we factor the denominator, and now we can do 2 geometric series. And now each one of them only has an x. It's going to be much nicer. So this is, again, a great general theme in mathematics. Much better to do a lot of easy problems than one harder problem. To do a lot of simple things rather than one bad thing. And so now when I expand this out with the geometric series formula, when the dust settles, we just get the following. And this gives us a great example of the power of generating functions. We started off with some objects that we wanted to study. We built them together. We got a new function g of x. And then by understanding global things of g of x, we actually deduce things about the fn's. And so the huge 30,000-foot bird's eye view of what we're going to try to do is something similar. We're going to be looking at L functions and trying to get that to give us information about the objects we care about. So we saw Binet from Fibonacci. So you can look at whatever you want in mathematics. We will look at things in the form, the sum n goes from 1 to infinity, an of f over n to the s. And the question will always be, what will be good choices of the a and s? And we will always require that there is an Euler product over primes of some local functions of 1 over p to the s that will depend on f somehow. And so we will say a lot more later about just precisely what these objects are. But the idea is to somehow take local data, form a global object, study the global object, and then use that to say some things about the local information. Or sometimes the global object has interesting properties of its own that we might want to study. Okay, any questions on what we've done up till now? Okay, so there should be a couple of Pavlovian responses. So the first is a product. You should think logarithms. How many of you have done complex analysis? Okay, how many of you have never done complex analysis? Okay, the next lecture will be a 30-minute to 1 hour, everything you need to know about complex analysis. So I have given this before. This is a lecture designed for physics majors, where you are willing to play a little fast and loose with the mathematics. So in complex, always good to do a contour integral. And anybody know what we should do a good contour integral of for those of you who have done complex? So we will see that if you do a contour integral of f prime over f, this has a lot of information that you can use to deduce things about the object. Now, what is f prime of z over f of z? It turns out that's just the logarithmic derivative. So it's the derivative of the log of f of z. So the logarithms come into play. This hopefully helps you understand why I insist that I have a product for my L function. Because I'm going to be doing logarithmic integrals. If I have to integrate the derivative of this divided by itself, that's a nightmare. But if I do the derivative of the log of, we'll call it LFS, well, the log of this, the log of a product is the sum of the logs. And that's actually going to be a nice quantity to study. So the logarithmic derivative is actually going to work out very nicely. So I'm going to end with one last thing, and then I will call it a day for the first one. So the way a lot of these problems work is you have some objects that you want to study. And you have objects that you can study. And so you need a way to relate them. You need some kind of formula that connects them. And this is where we get the explicit formulas. And so one of the biggest examples of things that we want to study is eigenvalues. So if you have AV equals lambda V, then lambda is the eigenvalue, and the non-zero vector V is the eigenvector. And I will send a link to a video on random matrix theory, which is another one of the possible topics. And the idea is you choose a large matrix where the aij's are somehow chosen randomly. Maybe you choose each individual aij randomly, or maybe you choose the matrix from some kind of group, maybe unitary matrices or something like that. We want to understand the eigenvalues of the matrix. The eigenvalues of the matrix correspond to the energy levels of some physical system, but it's the matrix elements that we know things about. And so what we'll see later is the trace of A is equal to the sum of the eigenvalues of A. And this is an example of an explicit formula. This is the eigenvalue trace lemma. And in fact, more is true. The trace of A to the K is the sum of the eigenvalues to the kth power. The hope is if know enough about something, it is uniquely determined. This is sadly a false hope. If I give you the function f of x is e to the negative 1 over x squared if x is not 0, and 0 if x equals 0, if you plot this function is essentially 0 near 0. And in fact, if you use L'Hopital's rule, you can show that all the derivatives at 0 are 0. This means the Taylor series of f is identically 0, which means the Taylor series only converges at the origin. This is not impressive. The Taylor series is f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared plus dot dot dot. Well, everything from here onward is a multiple of x. It has to agree with the function at 0. So the fact that the Taylor series converges but doesn't converge to the function is terrible. It means Taylor series are not unique. So why am I talking about this with matrix theory? Well, if I give you a probability distribution, it's non-negative and it integrates to 1. So the kth moment would be the integral of x to the k p of x dx. And the hope is that the moments uniquely determine p. You might have heard of the physics paper, can you hear the shape of a drum? If you know how something vibrates, does that uniquely specify the geometry? And the answer is no. You can't have two different shapes that have the same resonances. You can also have two different probability distributions that have the same series of moments. What's important to note here is that these are the moments where k is an integer. If you know the moments not just at the integer values, but actually along a sequence that accumulates, then by using some results from complex analysis, then you can uniquely determine the distribution. And so one of my advisors, like to say, using abstract nonsense, using these advanced convergence theorems, you can basically show that, everything goes the way you want. But we have to be careful because it's not enough to know just the moments. And why is this useful? Well, if you look at the sum of the eigenvalues of A to the kth power, this is essentially the same as the kth moment. of the eigenvalues. And we'll talk about that a little bit more. What you really need to do is just divide by the number of eigenvalues, divide by n, and that's essentially knowing the kth moment. So if we can connect this to the trace of a to the k, and if we can understand the trace of a to the k, we would understand the kth moment of the eigenvalues, and then that would hopefully allow us to understand the density that the eigenvalues are coming from, and understanding things about the energy levels. So this was meant to be, really broad, 30,000 foot high overview of the main ideas of what's going on. Is what are we looking at? What kind of objects? We're going to try to form functions where we combine local information to get a global object, understand the global object, and then deduce things either about that global object or about the local inputs. What are the techniques we're going to be using? We're going to be more on the analytics side, but we are seeing that we have to be extremely careful. The fact that functions like this exist is terrifying. There is a tremendous difference between real analysis and complex analysis. The way I like to phrase it is complex analysis is the snooty country club that only allows certain functions in. Real analysis is, oh, more the merrier, come on in, come on in. Well, it's great that more functions can come in, but because so many things are allowed, it's not that special to be in. In one variable calculus, how impressive is it to be differentiable? Well, in one variable calculus, to be differentiable, that means the limit exists essentially as I approach from the left or the right. It's really not that big of a deal to be differentiable. In several variables, it's not enough to just approach along the axes, or along straight lines, or even along a spiral. Any path you take. And so when I first started teaching multivariable calculus, I would have my kids who were in preschool or younger at the time, they and all their friends would draw stuff like this, like the Miyagi Karate Secret. And you have to be able to calculate the limit along a path like that and show that that limit is the same as all the limits over here. So it becomes incredibly meaningful to be differentiable in two variables over one variable. And to be complex differentiable turns out to be a much stronger condition than being real differentiable. And so a complex differentiable function has a lot of wonderful properties. All right, so in the next lecture, we will do complex analysis. And so I will give you the brief blitzkrieg introduction to complex analysis and show how you can convert a lot of integrations in complex analysis to just doing a Taylor series and doing some algebra. So it's wonderful that you can replace integrations with algebra. All right, I've got time for probably about like 1 or 2 quick questions if there are any before I have to run to a Williams thesis defense.